long-term sea level change at the coast. And among them, for example, shelf currents, small-scale eddies, atmospheric forcing and wind stress, trend in waves, density change in river estuaries and delta due to, for example, change in river runoff, changing tides, climate modes, and maybe other phenomena. So we can ask the question ourselves, the question, can we construct long-term coastal sea level time series using past altimetry missions, considering that obviously we have tide gauge in some location, but not everywhere, and in some region of the world, there are no tide gauge or no long-term tide gauge records. So we want to close the gap of about 10 kilometers along the coastal zone. And this was the objective of this ESA Climate Change Initiative Coastal Sea Level Project that started in 2019 and is continuing now since recently for 2 years until 2024. And its objective was to reprocess data from JSON 1, 2, 3 missions along the world coastal zone in order to answer the question, is coastal sea level rising at the same rate as in the open ocean? And you will see that the answer is yes and no. So the detailed objective was to reprocess along track data of this mission by retracking the radar waveforms and improve some geophysical correction, and I insist we focused on coastal trends in this project. So we use the ELS retracking method developed by Marcello Passaro, plus the associated state bias. We use the extract processing system developed at Lagos by the team of Florence Birol. So as already said, we focus on JSON 1, 2, 3. We use the long track high resolution data, so the 20 Hz data, which correspond to a spatial resolution of about 350 meters. So far, the temporal coverage of our data set is 18 years, started in January 2002, but we intend to extend it by at least 2 more years. And we made a strict editing in order to keep only very good data close to the coast. So these are the studied regions, almost all regions, not exactly all, because we miss the Baltic Sea and part of the Northwest Pacific. But this is already many coastal regions which have been considered. So here I show you examples of, so there is something, we cannot suppress the band here, but
to one second.
Okay, thank you. So here just a few results, a few examples of results obtained with this new reprocessing. So just here 3 cases. One, the top one is along the coast of China. You have this, I don't know if it is working, you have the satellite track here. And on the right, you can see the trend estimated as a function of distance to the coast, against distance to the coast. The coast is on the left, here, and the open ocean on the right, or offshore on the right. So in that case, you can see that the trend is almost constant, and the middle panel show you another example in the Mediterranean Sea, where you see a slight increase in the trend as the satellite approaches the coast, and the last example here is in the Caribbean region, where we see a decreasing trend as we approach the coast. So, I'm sorry, but it's blocked. We cannot. It's because of. Okay, so here you can see the distribution of the closest distance to the coast along the tracks that we obtained from this reprocessing. So on average, we get a median value of 3.5 kilometer, which is already a great improvement compared to classical data, graded data. But you can see also that we can, in some cases, we can go much closer to the coast, up to less than 1 kilometer. And here you have a map showing the distance to the coast of the first valid point along the satellite tracks. So we introduce a concept of virtual coastal station where we are able to produce a valid sea level time series at the coast at this location and associated sea level trends. So we came up with this reprocessing by more than 750 stations, virtual stations, located at less than 6 kilometers from the coast. And among them, 271 virtual stations located at less than 3.5 kilometers from the coast. And here you have a map showing this virtual station located at less than 3.5 kilometers from the coast. These are the green dots here. And we have superimposed on this map the location of the tide gauge station sites, for which we have available data over the time span of over our study time span, that is from 2002 to 2020. So you can see that in many regions, there are no tide gauge or no tide gauge record, and this virtual station complete very well or provide data where we have no data along some of the world coastlines. So we made a comparison with tide gauge, and here it's just one example at La Réunion Island in the Indian Ocean. On the bottom part, you have the two time series from tide gauge. I don't know which one. The blue is the tide gauge, and the red is altimetry sea level time series. So in general, we have a good agreement. And here is in terms of trends. Again, we have the altimetry-based coastal sea level, not coastal, sea level trend, again, distance to the coast is here. And the blue star is the trend computed with the tide gauge over the same time span. So we see a good agreement. It's not always the case, but here in such example, we have good agreement. Here I show you another example. It is in the Gulf of Mexico, where you have the satellite track here that cross land in the Mississippi Delta, and here the coastal sea level trends. What we see here, the coast is here, is that on average in this region the sea level trend is on the order of 6 millimeters per year, and we see this clear increase as we approach the coast, up to 10 millimeters per year. So we wonder if it was due to wrong noisy data, and we looked at the sea level time series for the first few points here. Qu'est-ce qui se passe? Ah, dans le micro. Ah, okay. Sorry. I am a bad student. So you can see here the sea level time series of the first 6 points from the first valid point here, the closest to the coast, and you can see that in general we have nice time series that are coherent from one point to another. And we see also a clear increase, in particular during the last decade. So we think it's a real signal and not noise, not noise. And this was more or less confirmed by there are many tigers in this region. Located here by the red stars. And you can see that depending on the sites, the sea level trend at the coast over the same period as our study period range from about 8 to 13 or even 15 millimeter per year. So our estimate of 10 millimeter per year here at this location is probably correct. But so far, we don't know what is the cause of this increase in the sea level trend close to the coast. So in the last 4 to 5 kilometers from the coast. So this has to be investigated in the future, in the near future. Here is some summary of our results, where we show on this map the coastal trend behavior at all virtual stations. So the white squares correspond to constant trends, that is, the trend does not change from offshore to the coast, while the red triangles, red and blue triangles, correspond to an increase in the trend close to the coast or decrease in the trend. The statistics are there. In more than about 90% of all virtual stations, we find that the trend is constant. And this was really unexpected because of the small scale processes that we expect to be active at the coast. But you see, in many cases, we see the trend is constant, which is, I think, an interesting result. On the other hand, in about 10%, we see this increase or decrease of the trend. And now I show you very quickly a few examples of quasi-constant trend from offshore to the coast. Here it is in the Mediterranean Sea. Here again in the Mediterranean Sea. We noted in several instances some oscillation. We don't know yet what the cause of that. Discussion with Sonia, I don't know where she is here. Earlier today, she said that it may be due to currents, we don't know. This is not seen everywhere, but this is seen in several locations. We have to, again, to investigate the cause of that. And here, this is a map of the 10% cases where the trend increased or decreased when we approach the coast. And show you briefly, quickly a few examples. Here it is along the coast of Western Africa. We see a clear increase in the trend from offshore to the coast. Another example in Eastern Africa. Here. Now I have two examples of a decrease of the trend. This is Madagascar. And another example in India. And so in some instance, we see this kind of behavior. So these, the data, the coastal sea level time series and the associated trends are obviously freely available. You can access the data from the SINOE website, which is the link is indicated here, and the data product and processing are described in at least in these two papers, but we publish a little more, and you can access them to have more information on this processing. So as I said at the beginning, we are starting phase 2 of this project now. And the objective of phase 2 are summarized here. First of all, we want to extend in time the sea level time series at the virtual station, at least 2 more years. Because we saw in the at the beginning of the project that adding 1 year or 2 years decrease the error or the uncertainty of the trend estimate. So this is very important to have the longest as possible time series. We want to also look at new geophysical correction. For example, we intend to use the newly released ocean tide model phase 2022, which has according to the author, better estimate of this correction in the coastal zones. And we also intend to use another retracking in the future, the adaptative retracking model developed at CLS. We want to better characterize trend errors related to both processing and climate variability, and in particular the influence of climate modes, and this will be performed by Julius, who may be here in the audience. And one important topic we want to focus on is to quantify the small-scale coastal processes at sites where we have observed that sea level trend at the coast differs from offshore. Okay, so how to quantify these small-scale coastal processes? This is a problem because I will come back to this figure, because in situ data with long-term time series are very limited or inexistent, or if they exist at some sites, coastal sites, they are not necessarily located close to one of the adjacent tracks. So it's a real problem. But we have some hope anyway. For example, for tracks that cross land in river delta or river estuaries, we can look at river runoff, and this will be the object of collaboration with Angelica Tarpanelli from ERP in Italy. And we will also focus on the effect of waves in collaboration with Sonia, who is here, who has developed high-resolution models for waves in some coastal sites. But we also want to look at other processes. Just to show you some very preliminary results about the possible effect of river runoff in one case. This case is Iriwadi River Delta in the Indian Ocean. So you have the satellite track here, and this is our estimated coastal sea level trend against distance to the coast. The coast is here as shown in the previous slides, and we see this slight decrease. So we checked that it was not due to erroneous data, noise in the sea level time series, and here we have the sea level time series from the first point here. So these are for the first 6 points, and we see that the time series look good, and there is some good agreement or good coherency from one point to another. So we don't think it's this behavior seen in the trend is due to errors. And from a recent discussion with Angelica Tarpanelli, with looking at river runoff, river runoff in particular at the coast, using satellite data and modeling. She provided us with some results at these two sites here, this site upstream the river, and this one which is closer to the delta. And here I show you the results of the river runoff at these two sites, and she found some slightly decreasing trend that could explain what we see in the sea level trend, because if the runoff, river runoff is decreasing, we are expecting a decrease in sea level trend. But again, this has very preliminary result, and we have to investigate in more detail this kind of processes. And finally, we also expect to use high resolution ocean models, but this is also at a cost. This is also not an easy task, because either the models have long-term time series, but not the required resolution for solving our problem. Just to show you an example here with a METC reanalysis from Siemens. So there are long-term time series, but the resolution is inadequate to explain what we see in the last 4 to 5 kilometers from the coast. There are some cases where the resolution is good. For example, for the Mars 3D model developed at Ifremer along the Corsica Island in the Med Sea. The resolution is 400 meters, but it covers only 5 years, so it's difficult. Another example here, the Symphony version of the Symphony model in the Gulf of Tonkin, developed by colleagues at Lagos in Toulouse, has a good resolution for our problem. It ranges from 300 meters the coast to 4 to more than 4 kilometers offshore, but it only covers 10 years. But possibly our colleagues will extend the output of their model to cover our study period. But I am still optimistic that we can find some models, and develop some collaboration with modelers to, at least in a few sites where we see this strange behavior in the coastal sea level trends. So I stop here. Okay.
We can have one question.
Yes.
Okay.
Then I'll try. It's not too difficult, the question. Of course, your list of possible causes of change of rate close to the coast were very good. There's one that was missing that I didn't see, was bathymetry. You know, if you have a steep or a shallow bathymetry, it must make a difference.
Yes, it's not. I did not include the bathymetry because it's not a process. It's good. It's not the morphology of the coast that can influence, impact some of the processes I showed before.
Yes. Okay. Let me then say bathymetry in relation to heating, because if you're going further from the coast and you have a deeper water, then your thermal part should be larger than close to the coast where you're shallow.
Yes. I fully agree with you. I explain why I did not include it in the list of processes.
Well, okay, but the heating wasn't there in relation to.
We started to look at the bathymetry, but so far we don't see any clear relationship. But again, all this work on the processes that are on the coast of the behavior we see is just starting. It's the object of phase 2, and maybe in 1 year we will come up with more concrete results.
Okay.
I agree. Bathymetry is an important.
But then in relation to heating.
Yes, sure. Yes.
Okay, thanks again.
We will have a change in the order of the talk. The next one will be Paolo Cipollini. He will be presenting dual band altimetry from the Copernicus Crystal mission, its capability for coastal altimetry.
Yeah. Yes. Yes. Of course, yes, we're struggling with microphones. So thanks very much. Thanks to the chairs and the other presenters in the session for accommodating this small change. And I apologize if I'll have to leave later. So, but it's a great pleasure to be here in the Coastal Altimetry workshop. And indeed, it's a pleasure to have the opportunity to tell you about this great mission that would be launched in 3 or 4 years' time, or actually in 2027, that's the plan at the moment. Crystal, one of the Copernicus expansion missions. It's a dual band altimeter. I'll tell you a lot about it in a moment, but in particular, we'll see what it can do for coastal altimetry. I should acknowledge my co-authors in ESTEC, in ESRIN, and the colleagues from UMETSAT. There'll be some contributions about how they're going to process and generate the ocean data, including the coastal data, later in the talk. But let me start from the one crucial thing I had to always say this to start first. It's a cryospheric mission. So it's an altimeter for the cryosphere. So the project manager always reminds me, the primary mission objective is ice, land ice and sea ice and the snow loading and so on. It's important because every year we are losing a cube of 10 kilometers of side, 10 by 10 by 10 kilometers. Every year is lost by melting. And the city that you see on the map is Paris. Okay, so ceci pour les Parisiens. That's just about half of it. That's the land ice that will increase your sea level. The sea ice, as a first approximation, doesn't change the sea level when it melts, but that's land ice, an artist's impression in Paris. So it's a Copernicus expansion mission, so it will be operational and continuous coverage up to a very high latitude, and it builds on the great legacy of Cryosat. Cryosat, an explorer, a perfect example of how an Earth explorer then generates an operational mission. And we will do things like monitoring the sea ice thickness all year round, which is being demonstrated with Cryosat. But today, let me tell you what can Crystal do for oceanography, and in particular for coastal altimetry and inland waters, because amongst the secondary objectives, there's also hydrology. So let's see how, starting from the legacy of Cryosat, with Crystal, we make it better. And it's not easy to make a better Cryosat, but we're trying to do it. So this is a little bit of a dense slide, but it's because we have a number of improvements on Cryosat 2 that Crystal will bring about. So first of all, it's a dual frequency altimeter, Ku and Ka together, SAR altimeter, and in fact, Ku is also interferometric, so you've got SAR-in Ku band. The Ka band is primarily added to measure the snow layers, so for a cryospheric purpose, objective, but it will bring some advantages, of course, for oceanography as well. We increase the bandwidth with respect to Cryosat, so we go to 500 megahertz in both channels, a better characterization of the interferometric baseline and more stable, and make it slightly larger. All contributes to a reduced uncertainty on the angle of arrival, which means that when you do interferometry, you get better measurements. Also, with Crystal, we can do open burst mode. We have a closed burst and open burst possible, both possible, which of course brings improve the resolution and range precision. We have flexible tracking. We can do open loop or closed loop. We will embark on Crystal the latest version of the AMR radiometer provided by our colleagues in JPL, and it's an inheritance from Sentinel-6 AMRC. So there will be wet tropospheric correction available on board, and also the high frequency channel that, as you know, are very useful, especially in the coastal areas, because the footprint is smaller. And we can probably also use the microwave radiometer to do a few nice things on the ice, but that's out of the scope of today's talk. And also we will cover everywhere, including all the hydrological targets, with different modes. So let me introduce a preliminary version 0, let's say, mode mask for Crystal. So you see the gray bit up there is sea ice. So you see land ice and glaciers. So the land ice mask includes all the glacier areas and the oceans, and all the rest of the land is called inland water, because the main thing that we're looking for there is hydrological target. And I should say now, but I'll repeat it later, that EUMETSAT, our colleagues in EUMETSAT will generate the global ocean products for Crystal, which includes the coastal area, and also the sea surface height into the leads in the polar oceans. So there's a big contribution expected to polar oceanography from Crystal. The different modes of operation, that's what it looks like. I tried to summarize it in a sort of metric form. So if we look at the columns first, so you see where we've got ice, an icy surface, we will operate it in SAR interferometry. So we will use the angle of arrival information to do interferometry. Where there's no ice, we will have it in simple SAR mode. If we look at the rows over the sea ice and iceberg, or the open and coastal ocean, at the moment we are planning to have open burst over the sea ice and icebergs area, and closed bursts over the open and coastal ocean, and over land it will be everywhere closed burst. It's remapped in this slide here, so you see all the different categories, so you can see immediately what are the different combination of SAR or SARIN and open burst and closed burst in this slide. And we are obviously trying to sort of accommodate things, because we've got a ceiling in terms of data rates that we can download at the moment. And you've got some estimates there at the moment. So you see the SARIN is quite demanding in terms of the data that you have to download, as you know, because it's much heavier. And SAR might not look much, but of course, I mean, we are now at the point that if we want to add something somewhere, a different mode somewhere, we need to remove it from another place. So this will probably evolve from now to when it's launched following the discussion that we're having with the community, of course. It's important to say once again that we can do open burst with the Crystal, which essentially it's about 3 times the number of pulses per second than in closed burst. So it's it's a large data stream, but it has the advantage that it will increase the precision, and also with a continuous radar chronogram, you can do proper, fully focused processing, so increase the data along track resolution, as you all know. And in fact, if perhaps I should go back, let me just focus for a moment on the big gray, light gray areas, which are where we got sea ice and icebergs. where we are in ESA-ESRIN and in open burst, because we are planning to use to take advantage of that particular combination of modes to have a more precise sea level anomaly in ice-covered regions, not only because you do open burst, but also because with interferometry you can take more than one lead and start trying to average. There was an example in a paper by Alessandro, which is quite clear, where you can see towards the bottom of the track in the figure that you can sort of take the signal from the lead, even if it is off native. And of course, with open bursts, we get lower uncertainty on the freeboard and the sea ice thickness. But this is a big advantage in general to polar coastal oceanography, but there are others. So we can monitor a number of different processes, ice shelf melting, polar ocean interactions, and so on. You can read them all there. In fact, this would bring advantages to coastal altimetry if we could afford the ESA-ESRIN in other places, which, like I said, would be a matter of perhaps negotiations a little bit down the line. I would like to show again past results that we've seen also in coastal altimetry workshop, like our colleagues in ESA, Pablo Nilo Garcia, already a few years ago showed that, looking at the angle of arrival and coherence, you can recover more or better measurements in the coastal zone. And the Danish colleagues in these papers were able to track the water surface in fjords. So it's quite relevant. Also, I should mention at this point that all these results are based on Chrysostat 2, where, in ESA-ESRIN, you've only got one burst every 4 for a number of reasons, whereas with Crystal, we are planning to have many more echoes, all the full bursts. But also, let me remind you of the fact, which I said already, that it will be a dual band altimeter. So we've got Ka and Ku together on the same footprint. So that brings in other opportunities. And we are seeking the engagement of the communities like this one to discuss what we can learn. One possibility is to look at the sea state bias. Doug Vandermark showed that OSTST, that little figure of the differences of sea state bias in Ka versus sea state bias in Ku. Now with Crystal, we will have data coming from simultaneous observations, not exactly the same footprint, of course, but simultaneous observation. And perhaps we can do an investigation of these surface-related effects. We are doing some studies on the ice component, sea ice, land ice, and inland water, which are here, but this is just to tell you. In a moment, I will tell you about the plans of our colleagues, new methods for the ocean science development. But this gives me the opportunity of saying that we are also developing a nice airborne altimeter, Ku, Ka, both interferometer, because we, for an airborne altimeter, we say, oh, let's have even the Ka band as an interferometric channel with a 1 gigahertz bandwidth, which we're planning to use for a lot of nice calibration and validation and preparatory study. This is being commissioned now. And I said before that EUMETSAT will be in charge of generating the ocean products. So let's see their plans for the marine data center. So exploitation of the Ku and Ka band for oceanography. I mentioned already the sea state bias, but there's 2 other important words there. For instance, you can get an improved ionospheric correction, improve the rain flagging of data. We've got to do some research and development here. And I'd also like to highlight at the bottom of this slide that the orbit which has been selected at the moment has got a number of interesting subcycles which are all useful for oceanography. So humans are planning to have thematic processors for crystal. So it's an operational mission. Those will churn out data in a sustained way, systematic, for the ocean, for the sea surface height into the leads, very useful for oceanography, for polar oceanography, and also over some large lakes like the Great Lakes. And also there'll be a processor for the coast, which normally in most of the world, if you look again at the mask, the mode mask, it's in ocean mode, but we might have a few areas where we run it in sub-interferometric mode. In the polar regions, along the polar coasts, certainly will be in sub-interferometric mode. And of course, EUMETSAT are building on a big product heritage. The products will resemble the Sentinel-6 products, and they will be produced in 3 different latencies. Near real time, which is a 3-hour latency, at least that's the idea at the moment, a short time critical of 48 hours, and a non-time critical still to be confirmed, but around 1 month, but will be decided later. And the important thing is here that the naming of the variables and the file naming should all be similar to Sentinel-6, so that should be used. It will be easy for the users to use these products. And this is equivalent to the timeline that I showed you before from ESA for the ice processors, the cryospheric processors, but these are the preparatory activities that EUMETSAT for the ocean processors, or the thematic processors that you've seen in the previous slide. So these activities are starting now, and the marine data center development should begin at the beginning of next year. And you see here there's a launch in quarter 2, 2027. It might be quarter 3, but however, yes, that's more or less where we are. And this is my final slide from the project, Crystal project perspective, where we are now. We've gone through a number of different reviews, the system requirement reviews, the PDR. At the moment, we are reviewing the system simulator, which also allows simulation of the performance of the instrument, which is quite promising. And we are in phase C, and the next big step is the critical design review of the system towards the middle of next year. But the good news that I can still tell you is that Crystal A, the first of the 2 Crystal satellites, is on track to be launched in late 2027, and it will be followed by after some time, possibly towards the end of life, or perhaps after 5 years and so on, by Crystal B. So it will be, we will have 2, but we will have only 1 operational at a given time. It's not a constellation of 2 meant to be flown simultaneously. There will be possibly a tandem phase where they overlap and we will calculate them. But we are on track for launching in 2027. So I hope I've convinced you that it's a great mission. It's certainly very synergistic with what we're going to learn from SWOT, and I'm more than happy, as I'm sure our EUMETSAT colleagues are, to get your feedback on ideas, on things that we could do, and things that we can add in our armory of algorithms to get the best out of Crystal data. Thank you very much.
Questions? Someone has a question?
On your slide, like the slide 20 on the products, you should just add what variables are you producing? Because you do it at 1 hertz, 20 hertz, and so on. I suppose you're producing all the variables that we've been producing with altimetry, with no exception, including waves and so on.
Yes, yes, yes.
And wind.
It's a good point. Yes, significant. We've had, Cryosat is giving a very good contribution to the significant wave height record. And with Crystal, I can only start to imagine what we can do because we have the two channels together at the same time. And it's probably, yes, thanks, Jerome. This is important to remark. Probably significant wave height is one of the geophysical variables on which we can learn most of the ocean from this dual channel approach.
With the seed bias,
Yeah.
and with the wave period, thanks to the fully focused star processing and a certain number of novelties. And not to frighten everybody, the numbers that you showed, 255 Mbps, the B is a small b, it's a bit, megabit per second.
Yes, yes, yes.
So you divide by 8 to have an idea of what it really is compared to your modem at home.
Yeah, megabit per second, yes. But the problem is that, there will be quite a lot of refinement in future months or years to find a nice mask. And the mask will be dynamic. Ideally, we can adjust it. Well, we have to include sea ice and also a larger portion of the ocean because we want to track icebergs. Perhaps I didn't mention it clearly, but the sea ice mask extends quite a distance in the open ocean because we want to track and follow icebergs.
Yeah.
So over there we'll have perhaps not so many icebergs, but we'll look at the ocean in open burst SAR interferometry, and it's probably going to be interesting in places like the Labrador Sea, where you've got interesting dynamics, and see whether from that particular model we can capture new measurements or learn more.
Unless if by 2030 it's a fully oceanographic mission. Joking. The other thing I wanted to say is that all the work that's done by this community, like all the new algorithm development and so on, are being funneled through an advisory group. Did you mention?
No, I didn't mention this. Yes, there's Crystal as any mission. Sorry, I thought perhaps it wasn't said about the other mission, but every mission that we've developed has a science advisory group, and there's a mission advisory group for Crystal that collects the user requirements because we have to somehow elect some representatives of the science community that help us. But this shouldn't prevent anyone to feed their comments and their ideas. So come and talk to me or Christina Martin-Puch, for instance, who's the representative of EUMETSAT in the mission advisory group. If you've got any ideas on how we could further develop crystal algorithms, or whether you can think of any applications that I may not have mentioned. It's particularly exciting. Let me say that it's one of the 6 Copernicus expansion missions. I find the Copernicus expansion missions particularly exciting because Copernicus is operational. They want to continue observations, and so we'll have the Sentinels next generation and so on, but those are, don't quote me on that, but those are a little bit more boring because you just get the optical instrument, a high resolution, and so on. The 6 expansion missions, of which Crystal is one, are great because they're born operational, so sustained observation, but in a sense they do novel observations because the technological evolution, like, having Ka and Ku together for the first time, will probably allow us to look at new things that aren't that operational. They're very much still at the research and development age, but I find this quite exciting.
Well, I will stick in the operational, so we can do better than less than 3 hours in latency, or you just put it to be in the safe side?
I would say now is probably in the safe side. There's Lotfi, the one issue that we've got is that how many stations we can get. So there's the satellite takes the measurement, and then it will have to download them. We can only do when it goes over a station. There's still a discussion on one station or two stations. I would probably be in favor of two stations, but perhaps our colleagues in EUMETSAT are more expert on this, and eventually they will be, I'm sure, ensuring that we get a latency fit for the applications. I should also mention that I didn't have in my slide, but over the cryosphere, we have a slightly less stringent latency. So for sea ice, what we call near real time for sea ice is 6 hours. So we get it quite easily. The ocean is more demanding for the near real time applications. So that's where we will have to do some work to make sure that everything is in place to get the data quick.
More questions?
Well, thank you.
Next speakers will be Julius in representation of Marcelo Passaro, and he will talk about Baltic Sea, new insight into the mean and variability of the sea level in the satellite altimetry era.
Thank you. So I gave this presentation already on Monday, so a lot of people might have heard it already, but those who haven't heard it, you might be interested in the work we did in the Baltic Sea project. So that's a ESA-funded project, and we worked on that together with some other colleagues from FMI, DTU, UCC, and DMI. And the objective of that project was to produce a regional optimized sea level product, incorporating innovations in pre and post processing, like coarse retracking, sea ice detection, and some more refined gridding approaches. So I'm mainly gonna motivate why we chose the Baltic Sea as a laboratory to improve sea level products. And then I give some examples, like 3 case studies about what we derived. So we derived a new mean sea surface, investigated trends and variability, and also did some investigations on a 3-day experimental high resolution grid, so high resolution in time. And overall, we provide like a gridded data set, so that's a monthly mean temporal resolving grid. And we also publish the long track data based on all the different missions contained. So that's the JSON missions, ERS, Soral, Sentinel, and yeah, most of the missions over the last 25 years. The Baltic Sea has some features which make it challenging to generate sea level data or generate gridded products. So it has very complex coastlines, there are many small islands and narrow straits. So we need some kind of dedicated coastal retracker and advanced algorithms to get information close to these coastlines. And also it's affected by occurrence of seasonal sea ice. So in the Bay of Bothnia, it's partially covered by sea ice in winter, and also Gulf of Finland. So if you want to know what sea level is like in winter, we have to detect or discriminate between ice and open water. And also a lot of variability is happening in winter, so that's important, of course, to understand the interannual to long-term variations in the Baltic Sea. So it's a perfect laboratory to study and apply some of these innovations in retracking. So we used an unsupervised waveform classification to discriminate between open ocean waveforms, lees, and sea ice. That was done by Felix Müller, and I think it's also applied in other data sets and in the Arctic zone or in areas affected by sea ice. And then also we applied some waveform retracking to improve the data closer to the coast and mitigate noise and errors in these waveforms. And of course, we have to calibrate the different missions against each other. So we did this analysis only for the Baltic Sea based on crossovers of different tracks, and it was applied based on the sea level anomalies after already incorporating all of the geophysical corrections. And we provided this grid at a relatively high resolution. The actual resolution is, of course, set by the smoothing length scale we applied here, and I think that was like 100 kilometer. So we validated this data, for example, against images where you can see here these different classified waveforms, the ice and the open water detection, and also we computed correlations against tide gauges based on the long track data, and also validated the gridded product and compared that for different distances to coast and how the performance decreased, and also comparing this to previous products or other available products in that area. Now, one of the outcomes of that project is a new mean sea surface, which we also compared here against a previous version like the GTU 15, and we see most of these differences in the coastal zone, which is expected because that product, to my knowledge, does not, or the product, the altimetry data on which this product is based does not incorporate like coastal improved data. And we can also zoom in here some areas where we see some larger differences. So that new mean sea surface provides a bit more smoother surfaces, so that indicates a better performance of the data in the coastal zone. Also, so that gridded data is then very suitable to study interannual variability and long-term trends, and that's why I also show some plots here. I'm showing these linear rates computed over the last approximately 25 years, and I also plot here tide gauge trends. So these are all absolute sea level trends, and tide gauges are corrected here for GIA. And yeah, you also see the uncertainties, which are also in a similar order of magnitude comparing the sea level data set and the tide gauge data. I will later also discuss some of these interesting patterns we found here, like the higher trends in the northern part of the Baltic Sea compared to the southwestern part, and what might have caused such pattern. And first of all, I show here a validation of these absolute sea level trends against tide gauges, which indicates that it performs slightly better than a gridded product, which also does not yet incorporate all of these innovations in data pre-processing. So they show you the RMS of the trend differences. It's a bit better. And also, as I said before, we wanted to understand why we have higher sea level trends in the Bay of Bothnia than in the southern part. So as this is a semi-enclosed basin, which is highly affected by wind forcing, we looked especially at the effect of inter-annual variability due to variations in wind forcing, which are correlated with the North Atlantic Oscillation, one of the most dominant modes of climate variability in that area. And we made a link of differences in sea level anomalies between the southwestern part and the northern part to anomalous wind forcing. And so these strong trend gradients might not consist in future, as this might be more not really significant due to the shortness of the overall period of observations, and it depends on if there is really a significant trend in wind forcing as well. One of the last applications I'd like to show you is experimental high temporal resolution grid, which we investigated because these data might also be important to study storm surges. And here I show like 3 different plots indicating the evolution of a storm surge, where of the silent storm surge in 2017, where we had pretty high water levels in the northern part of the Baltic Sea, and that signal kind of oscillated back to the southwestern part, leading to quite high water levels in that area. And yeah, we use the long track data to make this experimental 3D gridded product. So that might also be useful using these dedicated long track data. This product is published on the web, so you can access it, and I added here all of these links, and we also have a handbook description where you find more information of all the processing steps applied. And we also have a publication which focuses more on these investigations of causes of inter-annual variations, which is now also published. You might also remember these plots I showed you on Monday. For those of you who weren't there, you will also find on that website some codes, recommendation how to use the data and manipulate and plot some of these data contained what we published. So we believe that these activities can motivate future studies, and maybe we can also apply these processing steps to other regions in the world, which are specifically challenging to improve grids, maybe at higher resolution and at a higher quality. And of course, if you want to use the data, might be also interesting to study other variables like incorporating salinity and temperature, trying to study hysteric contributions and changes in the Baltic Sea. And also generally, of course, we have a lot of GNSS stations around the Baltic Sea. It's a good region to validate absolute sea level trends from altimetry because it can constrain these rates pretty well. And we've also seen that there are different institutes pushing forward new gridding strategies, and you might also even want to use the data to test alternative gridding approaches then, like optimal interpolation, maybe using machine learning or other alternative approaches. So thank you very much. If you have questions, get in touch, write the Baltic SEAL team or get in touch with me after the presentation. Thanks a lot.
Time for questions. I have one. Did you study the forcing or the driver of that trend in the Baltic, not only comparison between north and first and south? Because on your presentation you show why there is this latitude gradient in the trends, but did you look at the forcing of the positive trends? What is the cause?
No.
No.
So we did not investigate like the full sea. Or we did not compute a full sea level budget.
Okay.
Yeah, but of course that's kind of strongly connected to what happens over the shelf and influenced by mass changes there, and but it's might be interesting to do this, because I don't know if there's a study having close to sea level budget in Baltic Sea. I don't know. Okay.
Okay, so this concludes the presentation part. And according to schedule, we needed to further our discussion related to synergistics and climate studies and operationalization. So at this moment, I think I would like to invite all the session chairs to stage again and continue our discussion we started this morning. I think because in the first session of this morning, there were 2 cancellations. So we have to spend 40 minutes, and have the discussion.
Yeah. So I don't know if somebody want to add some comments to one of the point, one of the questions asked. No. So I had some feedback for the first point. Maybe Thomas is here on the room. No? Okay. So one idea to better promote also the product, the coastal altimetry product, is to try to work all together in a common project. So maybe find some projects that merge knowledge and input of different community and different applications to work together on the construction of a product or a game of products that can answer to different applications. But the idea is to have different people in the same project from different communities. So no comment on the other points? My co-chair maybe want to... Do you have something to add?
I was also thinking about to use the social media, that there are institutes or organizations that has the Twitter user or Instagram, and it's also a way to share the project that they are related with coastal altimetry, or even to promote this kind of workshop. That could be also to put more effort maybe in their social media.
As oceanographer, I feel obliged to come here to say my opinion about this first point. How to promote the support and support use of coastal altimetry towards the oceanographic community. Of course, meetings like those ones are very useful for us to understand the limitations and the potentialities of these kind of tools that you kindly develop here. So I think that it's a way of all of that trains, maybe more for students, but updating the pages and showing the potentiality of the products. I think that it's a right way to promote. I can give my example. I am here because of that. So I only can say that. Okay.
One idea would be that maybe there are people who cannot come here for whatever reason in different parts of the world, or they have other meetings, and maybe the virtual meetings also, where not just physical meetings, but also the virtual should be promoted more, or maybe YouTube videos on how to use. I think you have some probably already to how to use your product or how to get access, the latest at least, and it must be up to date. Might help people to use the products.
Perhaps, and Annie gave a very stimulating and interesting talk today about virtual network of altimeter stations for sea level monitoring. But from our perspective, probably we also need to think about in which aspect, like altimeter can really represent high gauge stations, and in certain aspects, we recognize, altimetry provide lots of information in the cross-shore, offshore, cross-shore directions, but because of sampling frequency and the spatial resolution, still there's a limitation, in measuring spatial availability, but in the time frequency, it's quite limited in terms of measuring actually like extreme storm surge and this, Also, we have had research showing that altimetry is able to provide very useful information about storm surge along the coast, but to a large extent, it's very opportunistic. So only if the track happens to pass by when the storm landed, and then usually you can catch good information for storm surge. But lots of time we only missed all this storm surge and only capture that part. So how we maybe need to use altimetry combined with ocean modeling, synergistically to assimilate those information into the model, then we somehow can produce something really close to what tide gauge can provide along the coastline. Oh yes, so just
I think to me the main limitation is the cross-track resolution. I think for many applications, for many scientific applications, even for sea level, looking at sea level rise or computing global coastal currents along the world coastline, we would need gridded data with the same resolution as we have currently along the track, but cross track. And this is impossible even in the near future, except with SWOT. I think only SWOT will be able to do that. So we have to wait for SWOT time series to fill the gap. But the other option, which has to be done in parallel, is, as you said, to use this along track data assimilated in an assimilation mode in high resolution models. But here also there's a lack of high resolution models everywhere along the coast, so we have to simulate modelers to provide to run their models not only over 2 years but over 20 years or more. So to me this is the main limitation, is the lack of resolution across the track, and the demonstration that with the available data we can do big science, I would say. Not only demonstrators, but bigger science.
yeah, I recall like several, maybe about 10 years ago. So we had like a joint workshop for the coastal altimetry community and the coastal ocean modeling community. And at that time, I think we attracted modelers come to this meeting, but seems in this meeting, we don't have a lot of ocean modelers or doing data assimilation attending, except, John Weir can give the talk, about his model for the US East Coast. And that was actually really impressive, and work. So, but certainly, I think in order to provide a product that easily for user to use, is we needed to, combining with a model and then provide some similar gridded product. Then it would be easier to use. I remember for satellite altimetry, when 20 years ago, once if it's a long track product, lots of oceanographers wouldn't use at the beginning. But when you have the gridded altimetry product from Aviso, then in the deep ocean community, this is really got very widely used because it's easier to use. You don't need to understand altimetry at all. You just treat it as a sea level, and it's very easy to use. So if in the coastal, altimetry product, we can also develop very similar products, then certainly, lots of people will use the product in all their research and their applications. Yeah.
Regarding this question there, coastal current observability. I think this community and the very useful, these Altimetry products, but I think that we have to be very careful extracting currents from the along track, the altimeter readings, records in the coastal regions, because we have, of course, we only measure slopes along the track.
Yeah.
So we have to assume that currents that we derive from there is geostrophic. And geostrophic means that it has to exist a balance between the pressure gradient and the Coriolis force. And of course, in coastal regions, you have a lot of other forces. The drag from the bottom drag, wind, the rivers discharges, etc. So hardly the currents are geostrophic. It's very difficult to understand that they are geostrophic. They have, of course, a geostrophic component, but we have to be very careful. Look, the altimeter products far from the coast is widely used by the oceanographic community. Very often and it's very useful. But close to the coast, you have to be very careful with that. Another thing that's about difference of trends between the sea level, the coast, and the offshore region. There is a strong debate in the oceanographic community about how is upwelling increasing, decreasing due to due to the global. And there is no consensus about it. But of course, coastal upwelling is a coastal phenomenon. And of course, if it brings cold water towards the coast, the sea level will decrease. And the behavior of the sea level close to the coast and offshore, it's quite independent because of this coastal, of course, in the regions where we have upwelling. It's not all the coast of the world. So it's an idea because it must be I was thinking about that, very important because coastal regions have different behavior. Thank you very much.
Yeah, thank you. Yeah, very good comments. So, Anne, do you have?
I thought that was an interesting point. I think as coastal ocean modelers and just physical oceanographers in general approach a lot of the problems that they're interested in, they're thinking about much smaller timescales. And so they will optimize their models or their observational campaigns not to try and measure or simulate the climate signals. And one of the constraints on that, and I'm not saying it's the right thing, we need to pay attention to these climate signals as well. How to do that, I don't think is super well worked out. And I think we're at the nexus of it right now, actually. But I was going to say that, shoot, I lost. Okay. And so in designing these experiments with your model or your observational campaign, you focus on these processes, and then you have to think about the constraints that you have on your resources. And that would include computational time. And so if you're getting down to these really high resolutions that are required at the coast, simulating a 30-year run is not feasible in a lot of cases. And of course, we are getting there. We're being able to have faster compute times and more resources with cloud services and things like this. But I just wanted to put that out there as like the perspective of the other side.
Any other comments? So I think we already discussed a lot about these different questions this morning. I don't know if we need to maintain the discussion, but if nobody wants to add No other comment? Okay. Should we close the discussion? Yeah? Okay. We close.
Yes. Otherwise, I leave everything for the internal website. Yes. Slideshow. This one, and this one, because they are very still preliminary and published, and it's not from me, so I. Guarda. Okay. So it's okay. You can.
Very interesting. I think it gives some perspective.
Yeah.
Maybe it's look at the wind.
Yes, McQueen's, yes, is what
Long-term trend.